Hey guys, welcome to ANS lecture number 4. Number 4 of 12. No, just kidding, there's not going to be 12. Maybe there'll be 5. I don't know. Anyway, let's talk neurotransmitters. We've already hit this a little bit. We talked about the fact that at our ganglion for both the sympathetic and the parasympathetic pathway, we are going to have acetylcholine released by the preganglionic neuron. Then the postganglionic neuron is going to release norepinephrine in the sympathetic pathway, and the parasympathetic postganglionic neuron releases acetylcholine. So those are our basic neurotransmitters. Now, the neurotransmitters have got to bind to receptors. The receptors that bind to acetylcholine are called cholinergic receptors. I'm going to have those on every place where acetylcholine is released. So my postganglionic neuron has cholinergic receptors because my preganglionic neuron released acetylcholine. Same thing right here. My postganglionic neuron has cholinergic receptors because my preganglionic neuron releases acetylcholine. Now there will be no cholinergic receptors in this path right here, because no acetylcholine right there. But in this path, postganglionic parasympathetic, releasing acetylcholine onto a cholinergic receptor. Now, I'm also going to find a cholinergic receptor on skeletal muscle, because remember from a while ago, somatic motor neurons also release acetylcholine. So, cholinergic receptors are for acetylcholine. And as you've probably gathered by looking at these labels here, there are more than one type of cholinergic receptor. There are nicotinic cholinergic receptors. Let's go back for a second here. Nicotinic cholinergic receptors are found on my postganglionic neurons and on my skeletal muscle. The skeletal muscle and these two postganglionic neurons, their job in response to the acetylcholine is going to be to generate an action potential. So acetylcholine has got to make this neuron fire an action potential. It's got to make this neuron fire an action potential. It's got to make the skeletal muscle do the same thing. So, bearing that in mind, if we look at our nicotinic receptor embedded here in the plasma membrane, our nicotinic receptor, it is a sodium channel. When acetylcholine binds to it, it opens up. Sodium rushes in, we get a depolarization, we get a graded potential, which we know graded potentials can lead to action potentials. Now, you might be wondering, why is it called a nicotinic receptor? Because not only does acetylcholine bind to these guys, but nicotine does as well. And this is one of the reasons why nicotine has many of the effects on the body that it does. All right. Our other type of receptor for acetylcholine, our other cholinergic receptor, is called a muscarinic receptor. And let's jump back 2 slides here. I'm going to find my cholinergic muscarinic receptor on my target tissue. So in other words, I'm going to be finding that on cardiac muscle, on smooth muscle, and on glands. Now realize that's a lot more complicated than just having it on a neuron or skeletal muscle. Well, the glands need to secrete. The smooth muscle needs to maybe contract, but also maybe relax. Cardiac muscle, maybe it needs to speed up its rate of contraction, maybe it needs to slow it down. So there is a much more complicated result that has to happen when acetylcholine binds to a cholinergic muscarinic receptor. And if we look here, there's a lot more going on here. We're not going to try and learn all this, but realize when acetylcholine binds, it creates, depending on the cell, these messengers inside the cell. And then those messengers, well, they might cause a gland cell to secrete. They might cause a particular smooth muscle cell to contract. They might cause another particular smooth muscle cell to relax. All right, so those are our basic types of cholinergic receptors. Let's ask ourselves now what acetylcholine does. We know that at the ganglion, acetylcholine causes our postganglionic neuron to fire an action potential. But on the target tissue, it depends on what target tissue we're talking about. Acetylcholine makes the rate of cardiac muscle contraction go down. In other words, it slows down your heartbeat. Acetylcholine causes the smooth muscle in the urinary bladder. This is the urinary bladder of a gentleman here. It causes the smooth muscle of the urinary bladder to contract. Acetylcholine causes the salivary glands and other digestive glands to make their digestive secretions. Acetylcholine causes the smooth muscle in digestive organs to contract. So these are some basic things that acetylcholine can do depending on what target tissue we're talking about. All right, now let's switch it over to the receptors for norepinephrine. They're called adrenergic receptors, and that word is used because not only do they bind to norepinephrine, they also bind to epinephrine, and another word for epinephrine is adrenaline. So I'm going to find my adrenergic receptors on my target tissue. So again, cardiac muscle, smooth muscle, and glands. And there's actually two receptor types, alphas and betas. We're not going to get into the differences between those two, but we should know at least that they exist. Okay, well, what does norepinephrine, or epinephrine for that matter, do to these adrenergic receptors and thus do to my target tissues? Well, my cardiac muscle, the muscle cells are going to contract more forcefully and at a greater rate. My smooth muscle in the urinary bladder is going to be inhibited. The smooth muscle in the guts, the digestive smooth muscle, also inhibited. Digestive secretions are going to be reduced and inhibited. That's not all. Norepinephrine will cause the blood vessel smooth muscle to contract, and that will raise your blood pressure. That's good in a fight or flight situation because higher blood pressure drives greater blood flow. Sweat glands will start sweating. Where's the sweat gland? There he is right there. Arrector pili muscles will contract. The smooth muscle in your little airways, your bronchioles, is going to relax. That's good in a fight or flight situation because we're dilating our airways, which allows more air to get in and more air to get out. Okay, awesome. Let's end this one right here because I only got 1, 2, 3, 4, 5, 6, 7, 8. 8 more slides to go. So I'm going to quit right here. There we go. Pick up next time for the last ANS lecture. I'll see you guys then.